This is video 23 on the reinforcement of concrete slabs. After video 23, we will talk about strut and tie models and about columns. In this video, we will give 3 specific examples how to deal with the method of yield lines. The first method is about the riddle of the sewer cover. This is a circular slab hinged on its edges and is loaded with a point load P in the middle. The question is, what is the maximum bending moment generated by this point load? We use the method of virtual work done. The external energy E done by the loads moving equals N times delta, but N is P, so you only have the load P times its displacement in the direction of P, which is delta. So E equals P times delta. The internal energy D dissipated by the rotation about the yield lines. Remember that for a circle, that the yield lines are a fan, is a fan construction, because in every point around the circumference, there is a tangent, which is a rotation axis. So you have an infinity amount of rotation axis, and the yield lines are a fan-like situation. So it means that every yield line projected to the axis of rotation, it means in fact that the total length by all the yield lines is the circumference of the circle, which is 2πr, when r the radius of the circle. So m is the plastic bending moment times 2πr times theta, which is delta divided by the maximum distance, which is r. E equals d gives us that the bending moment is the total load divided by 2π. This is strange. So the bending moment is independent of the radius of the slab. We call that the riddle of the sewer cover. How is that possible? We don't trust that, so we will check it out. We'll check it out with a finite element method, and you see immediately in the color code that yes, indeed, the bending moment is identical, even if the radius of the slab is changed. Moreover, the value, the total moment volume, is the load P, the load 1000 kilonewton is used here, divided by 2π, which is 160 kilonewton meter. That's what we should have had. But when you use the final element method, you will see it's 161 kilonewton meter. So it's almost the same. A second example is what is happening a lot is that you have a slab, and afterwards you have to make an opening in it. And then the question is, how large can we make this opening? And are we now influencing the loading capacity of the slab, yes or no? We can make now a simple approximation. You take a square slab, simply supported on all sides or hinged on all sides, and you make an opening in it, a reservation in it, which with dimension A, and the size of the slab is B. Then you would see that your yield lines, it will be normally like that, but yield lines stop at the edge of the slab, so there are no yield lines in the center. It's only those 4 short pieces. At ultimate limit state, you see that you have a mechanism, so we can be confident that the yield lines are more or less correct. We calculate the external energy expended by the loads moving, and we have now 8 triangles and 4 rectangles. So 8 triangles means 8 times delta divided by 3, and then the load on one triangle, of course, is this amount. It's b over 2, b minus 8 over 2 times b minus a over 2, half of it, times q. And for the rectangle, it's delta divided by 2 times the load and times the surface of this rectangle. You can rearrange your equation and you've got this equation. D, the internal energy dissipated by rotation about the yield lines. You take the yield line, project it to the x of rotation. That gives you a length by b minus a divided by 2, which is that. That's the m multiplied by it, and multiplied by theta, which is delta divided by the longest distance, which is this distance. So it's divided by b minus a divided by 2. And this you do it 8 times. This line is projected to the left, to down and to the right. And the same happens with the 4 corners. So you have 8 of those 8 parts to contribute to the amount of d, and you have 8m delta. You make E equal to D and you find M, and M is Q over 24 M times this. This is your bending moment of your slab with a size B and reservation with a size A. We substitute, we create a parameter S, which is A over B, which gives you the relative scale of the opening in your slab. And you substitute in this equation, and then you've got this one. And now we will compare what will happen. You will compare it to the situation when there is no reservation in the slab. And we call this maximum bending moment M0. So this is the bending moment without slab reservation, or when S is 0. When A is 0, then there's no reservation. So when S is 0, then you got M0. And M0, we know that when there's no reservation, a square slab has maximum bending moment for yield lines equal to QB squared over 24. And now we can make interpretation of this equation. When the bending moment is larger than the initially bending moment without reservation in the slab, or this amount must be bigger than 1, or S must be smaller than half, so A must be smaller than B over 2. This means that the bending moment increases at the reservations smaller than B over 2, not larger, smaller than B over 2. So if you make a reservation of a slab, make sure it's larger than a size B over 2. Then your bending moment will not increase and your existing reinforcement will fulfill this task. But once the hole or the reservation that you made is smaller than B over 2, then the bending moment increases. And the bending moment is maximum when the size of the reservation is B over 4. And this maximum bending moment is then 3QB squared over 64, or you will increase the bending moment with 12.5%. So if you have an existing slab with existing reinforcement in it, then you will overload the reinforcement with 12.5% if you make a hole in the slab equal to the size of the slab divided by 4. Suppose that you have a carport with a flat roof on it, and the flat roof is supported by 4 columns, and it's a square roof slab, 5 meters to 5 meters. And you want to know what is now the maximum load-bearing capacity, mobile load-carrying capacity of this slab. Or you can put it otherwise, you can say how much water can this flat roof slab, can this roof take? How much centimeters of water can it take? We have a normal slab thickness of 160 millimeters. It's environmental class EE3. So the concrete cover is 35 millimeters. We use a normal concrete C30-37, and the reinforcement is diameter 10 at 150 centimeters in X and Y direction, or 524 square millimeters per meter. So a normal slab, nothing peculiar about it. What is now the load bearing capacity? We will use yield lines because we want to know what is the upper limit, what is the upper bound. We will calculate the maximum capacity on the slab using an upper bound method because we want to have the maximum load bearing capacity. And therefore we use the method of the yield lines. The effective depth in the X direction of the first layer of reinforcement is the total height depth, or the total depth of the slab minus the cover minus the point of gravity of the first layer of reinforcement. It's 120 millimeters. The effective depth of the second layer of reinforcement is 110 millimeters. We know, because we've set in this example, that the reinforcement in X and Y direction is the same, and we know that the lever of the effective depth in X and Y direction is different. So that means that mu is different from 1. That means that the plastic bending moment in the X direction is different from the plastic bending moment in the Y direction, and we will take care of that in our calculations. So we will say that the bending moment in Y direction is mu times the one in the X direction. We know from the previous slides that mu is equal to this proportion, so it's equal to 110 divided by 120. Then we look at the axis of rotation. We have taken them at 45 degrees because of the symmetrical situation of our problem. In reality, you should call this angle alpha. You should make the calculation, and then you should optimize your problem according to alpha to find the maximum bending moment. But because of the symmetry, we know that the alpha will be 45 degrees. Then we take the yield lines. When the axis of rotations, when they cross, then you have a point. Sorry, when the axis of rotations they cross, they have a point there and a point here. You make an auxiliary line, and then you know that the yield line stops at the edge of the slab, and then the same in the other direction. We call in this direction X, you can also call it Y, it doesn't matter, it's the same. You call it X, and the other direction Y, and then we can calculate E and D. E, the external energy. Well, it's simple because it's all squares, so it means it's the total surface of the slab multiplied by its load Q, which is not known yet, and multiplied by the mean deflection, which is delta over 2. To calculate D, the internal energy dissipated by rotation about the yield lines, we have 4 times, because you have 4 axes of rotation, you have 4 times my directly projected projected perpendicular on the axis of rotation, and we call this distance from there to there, we call S. So that means my then projected directly on that, this piece of is S divided by 2, and then multiplied by theta, and then you have mx also directly projected on this axis. It's S over 2 times theta, and you got that 4 times. So this dimension S is equal as this dimension V. It's equal, and V is S. And from the geometry, S is equal to 5 divided by the square root of 2. So this is the one portion of the slab, rotate over angle theta, and this is the distance delta. And we know that delta is equal to theta divided by S. So now we can, the internal energy D, we can reorganize it, we can calculate it further. We substitute the S, or the theta, sorry, we substitute the theta, and we get this formulation, and then we know that my is equal to mu mx. This gives you the new definition of the new definition of D. Mu, we know it's 11/12, so D is equal to this amount. Then we can say E is equal to D, and when you work it out, you find mx, and mx is, let's say, 3.3 times the load Q. It's a very simple formula, and on the first phase of it, you say, oh, we have a problem in dimensions, because this is kilonewton. So what's happening? Well, it's not a mistake, because mx, remember, is always expressed as kilonewton meter per meter width. The slab is always calculated per meter width. So you have kilonewton meter per meter or kilonewton. So don't get extracted from that. So mx, we know that the bending moment is equal to 0.9 times the effective depth times the yield strength of the steel times the amount of steel, and we should divide by 1.1 to have a safe amount of steel in it. So what we do is the amount of steel rebars that are present, we divide it by 1.1, and we only take or calculate the load capacity with this amount of steel. We fill in the different parameters, and we find that the slab is designed for a maximum plastic bending moment of 22.37 kilonewton meter per meter. But we have calculated that the bending moment is 75 divided by 23 Q. And Q we can get out of this equation. When you put this equal to that, then we know what Q is, and Q is 6.86. So the total design value of the total load capacity, load bearing capacity of that square slab is 6.86 kilonewton per square meter. But this is the proper weight of the slab times 1.35, because this is ULSP. And that was the question. We are looking for the live load, the mobile live load, QM. And then we can calculate QM. And QM is more or less 1 kilonewton per square meter. So this roof can only take 10 centimeters of water, which is not a lot. That's why you put a roof, even how small it is, always under an angle, so that there is no stagnation of water possible. Otherwise, you will damage your roof very quickly. You can also, now we used this definition of mu, and we used the case that the reinforcement in X and Y direction were the same, but you can also calculate it in another way. You can use the method by taking mu equal to 1 instead of mu equals to 11 divided by 12. When you do so, then you have to calculate the reinforcement in the X and Y direction with a lever arm, not dx and dy, but with a lever arm which is a weighted average. The two methods are similar, but we will show just now, if we use this method, what will be the outcome. So the weighted average of the effective depth is then equal to 115 millimeters. Now is m equal to mx and equal to my, because mu is 1. We calculate E again, we have calculated D, and we find that m is 25/8 times Q. And now we calculate D, and we know that m is equal to the reinforcement divided by 1.1 multiplied by the yield strength of steel and multiplied by the lever arm D. The D now is this D, is the weighted average. And then you see that the bending moment is 21.44, and Q, the maximum total load of the slab, is 6.86, which is exactly the same as in the previous method. So you can choose between the two methods how to tackle the problem.